Okay, welcome everybody to week 4, day 2 of quantum physics for everyone. Today we're going to continue discussing interference, both classical and quantum interference, and we'll be demonstrating those using interferometers. In the first part of the session, I will be discussing the theory behind interferometers, and then we'll hand it over to Henning Weier at qutools, who will do some very nice experiments with quantum interferometers. So to review what we did last time, we discussed the Mach-Zehnder interferometer, which consists of two glass cubes. Essentially, they're called beam splitters, but they're made actually by taking two glass prisms, one coated in blue color, one coated in red color. Of course, in reality, they're both transparent, but you glue those together, and depending on which prism you put on which side, they're little slightly different prisms, you get a different phase shift depending on how you transmit or reflect from here. So this is showing if you block one of the paths, you get equal power out of this prism. And if you block the other path, of course, you get equal power out this. So these are 50% beam splitters. Okay. I think I missed a, well, let's just go on here. So we introduced the idea of phase, and this shows a traveling wave. It could be a light wave or a water wave or anything. And it travels to the right, and it has positive peaks, shown here, and negative troughs, which are marked in this cartoon as solid line and dashed line. The whole pattern travels to the right at the speed of light. The distance between two peaks is called the wavelength, or lambda, and the half of that is the distance from the peak to the trough, that's lambda over 2. In the reading, it was pointed out that in quantum physics, the wavelength of a quantum wave is equal to Planck's constant h divided by momentum. And momentum, of course, is, for an electron, momentum is equal to the mass times the velocity. But for a photon, the mass is 0, so you can't use that same formula. But there is a different formula for photons, and a given photon does have a certain amount of momentum. So this formula applies as well to photons. This is called de Broglie's relation. Okay, so then we also introduced the idea of phase clocks. These circular diagrams with an arrow are called phase clocks. They do not represent the quantum state itself. Quantum state arrows are drawn in a square grid pattern. So actually, to define this quantum wave, you have to know the quantum state, for example, the polarization, which in this case I show as vertical, but you also have to keep track of the quantum phase. And notice that at a given time, this is a snapshot of the wave, the phase is different at different points in space because the wave is up, down, or positive, negative, positive, negative. But then as this whole pattern propagates to the right, all these phase clocks move along with the pattern. Therefore, if I sit at one position, say I just fix myself right here and watch the wave go by me, if I watch the phase clock at this point, it'll be rotating around and around like this, around and around and around. Okay. Now also the wavelength of light is in vacuum, it's given simply by a relationship to the frequency of light. But if you put that same light into a piece of glass, glass has a refractive index, which is greater than 1. And this leads the wavelength to be slightly smaller. Okay, so this just shows the different phase relations, values 0 and 180. Okay, so this is a simplified cartoon showing how the asymmetric beam splitter affects the phase. Phase of transmitted light is always unaltered. It just goes through peak, trough, peak, trough, peak, trough, peak. And also, if you reflect from blue side and come out the blue side, there's no phase shift. So peak, trough, peak, trough, peak, trough, peak. Okay, but if you transmit or if you reflect from the red side to the red side, you get a 180-degree phase shift. So peak, trough, trough. And you can see here, one of the beams is a solid line with a 0 phase shift. The other beam is a dashed line with a 180 phase shift. So this beam would cancel out the 0, and there would be 0 power coming up here. Okay, so here is a zoom pole, and let's see if the zoom poles are functioning. Looks good. Let's do this zoom pole right here. Notice that this second beam splitter is flipped relative to this first beam splitter. So at this point in space, specify the phase of the light that came from path 1 to here or path 2 to here. And remember, 0 degrees means there's no phase shift. And remember that when light transmits, there's no phase shift. And if it bounces off of the blue to blue side, there's no phase shift. So start from here, work it out, and then start from here and work it out. I'm going to end this poll. So it turns out that there still was a widespread of answers. So I'm going to walk you through this, which we also walked through last session. So starting in path 1, we start with 0 phase here because that's a solid line. Then if we reflect off, there's no phase shift. So starting at 0, 180, 0, 180. So the first one has to be 180. So the answer is either C or D. Let's try the next one. Solid line means 0. So 0, 180, 0. So it's 180 and 0. So I just realized that perhaps a better way to count this off, instead of saying peak, trough, peak, it's better to say 0, 180, 0, 180. Or if there's a phase shift, like down here, there's a phase shift here, you could go 0, 180, 0, 0. Because without the phase shift, it would have been 180, but now you flip to 0. So 0, 180, 0, 0. Whereas over here, you're transmitting, so it's 0, 180, 0, 180. Okay, with that, let's do the second zoom pole. Zoom pole number 2. Again, you don't have to start all the way at the first beam splitter. Just start here and then start over here. I see there's a chat question. There's no phase shift when the light transmits. In either orientation, when it transmits, there's no phase shift. You only get a phase shift possibly if it reflects. And that's only when you reflect red to red. So it's 0, 180, 0, something. And here it's 0, 180, something. Okay, we have pretty good results now. Most people said D. Let's see if we agree with that. We do, because this is 0, 180, 0, 180. Whereas this one is, 180, 0, 180, 180. Because it's red to red, so it flipped. Okay, so that's the idea. Transmission always gives no phase shift. Reflection can give a phase shift or not, depending on which one it went through. So there won't be an exam, so don't worry if you didn't get all those. That's just the idea of it. Now, let's talk about neutron interferometry, which was in the chapter you were meant to read for this session. Neutron's like an electron. It's a little massive particle, but it doesn't have any electrical charge. Therefore, it interacts less with matter. So it could be good for sensing certain things. In other words, it won't just respond to electric charge, but it could respond to other things. In fact, you might know that electric forces are enormously more strong than, or stronger than gravity. Therefore, if you want to sense gravity, the strength of gravity, you should use a neutral particle because it doesn't experience any electrical forces. Okay, so the point is here that you have a neutron beam, single neutron comes along. When it hits this silicon crystal, you can see these little silicon wafers here. These wafers are carved out of a single crystal. This giant thing is a human-made single crystal of silicon. To good approximation, every atom throughout this entire crystal is oriented correctly in a perfect lattice. And they carved them out of a single block here so that there wouldn't be any, motion of these relative to each other. Because silicon is also very brittle. It's very stiff. Okay, so neutron comes here. When it goes through one of these silicon plates, there's a bunch of atoms in there which are lined up in a periodic array. And just like when light reflects off of a butterfly wing, it can impart, diffraction effects. For a butterfly wing, you see colors, but here's a neutron, so there's no colors. But the diffraction caused by the array of atoms can cause the neutron to deflect at a very well-defined angle, say, 20 degrees. Or the neutron also has a certain probability to go straight through without deflecting. If you put two detectors here, you'll see about a 50-50 probability that the neutron will be deflected or not deflected. So this acts like a beam splitter for neutrons. Now, if the neutron comes here, it can either go straight through or it can deflect. If the neutron goes here, it can either go straight through and be lost or it can deflect. So these two paths now can recombine on a third crystal. So this neutron path can either go straight through to detector C2 or it can deflect to C3. And this neutron path can go straight to C3 or deflect to C2. So you see it's a perfect Mach-Zehnder interferometer. Now here's the point about gravity. The neutron has a certain initial speed, same speed. Let's assume it doesn't lose any speed when it goes through the crystal, same speed. Now, but if it starts to go up, it's like climbing a hill against gravity. It decelerates, it slows down. And then if it gets deflected, now it's going on the level again. So whatever speed it had when it got to this point, it maintains that same constant speed over to here. So here it's going, say, fast, and then it slows down, and then it goes slow. And here it's going fast, 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 and it slows down, and it's going slow. So no matter what path it takes, it eventually ends up going slow, whichever path it's in here. It could take two paths and end up going slow. But the point is that in this path, it's going fast. In the AB path, it's fast. In the CD paths, it's slow. And in these upgoing paths, it's transitioning from fast to slow, fast to slow. Okay, that's all the physics. So here are the three gentlemen who did this experiment in 1975. I was a graduate student studying for my PhD and taking a course in quantum mechanics at that time. And I remember that my professor was really excited about the publication of this experimental result, because it was the first time any experiment had shown that gravity can affect quantum probabilities. Very nice result. Here's the crystal that they used again. And then here's the apparatus. You see there's a neutron beam coming left to right. It comes out this little hole here, hits the first crystal. It can go straight and then straight, or it can go straight and deflect. And here's the second crystal. So here I animate and illustrate these paths through these three crystals. So here, if it goes this way, it's lost to the interference experiment, but we can monitor that. If it goes this way, it's just lost into the wall. But if it deflects both times, then it can go to the third crystal where the quantum interference causes state vectors to, combine in a certain way, A plus B or A minus B. And then at the detection, we get the interference effect. It may arrive here, not there, or vice versa, with different probabilities. So let's say we run this experiment for a while and we see there's a certain fraction, let's say, 25% coming here at the upper detector and 75% coming here at the lower detector. Now, remember, gravity is making it slow down when it rises up, because we're looking from a side view here. We're not looking from a top view. This is actually a side view. So when it goes up here, it's actually rising up against gravity, slowing down, and now it's moving slowly. Here it's going fast, and then it slows down against gravity. Now it's slowed, and then it recombines, okay? So we have 25, 75, but the amount by which it slows down depends on the strength of gravity. And gravity is determined by the density of the Earth right under this apparatus. So it turns out if I were to drive a truck and park it right under this apparatus, the truck contained, 1,000 tons of lead or 1,000 tons of gold. It would change the strength of gravity in this region. It would make these particles slow down even more than they had slowed down without this extra mass down here. Therefore, the difference of the speed in this upper path and the speed in the lower path would be greater than it had been before. As I tilt this angle higher. And the periodicity, the period between these peaks, these are not the peaks in the quantum wave. These are just the oscillations of the interference pattern as you tilt the apparatus. But the separation between these maxima will depend on the strength of gravity, which depends on how much mass is down below it. Very nice. Okay, so that's sort of how it works. You can use it to measure the strength of gravitational field. You can also use it to do other things, it turns out. So with that introduction, let's run a zoom poll. So here's the relation, the wavelength, the larger the momentum is, the smaller the wavelength is. Okay. So here we're going from A to C. That's part of the question. We're rising up we're starting at fast and we're ending at slow. We're trying to compare that to the change of phase in the BD path. But we're starting at fast, ending up slow. So from what I just said, what's going on in the AC path is the same as what's going on in the BT path, BD. In both cases, you're starting from fast and you're ending up at slow. So you're changing the phase, many times within here, but what's going on in these two paths is the same. So let's just run the poll again. 5 seconds. Okay, we'll end the poll. Very good. Okay, so almost everybody said C, which is correct, the same phase change. So this is a little bit tricky because the phase is gradually changing. See, before we've only talked about sudden changes on reflection, but here there's a certain wave phase. The phase clock has a certain angle or phase value. And as you gradually rise up here, you gradually slow. So the wavelength is gradually changing. So you're accumulating a certain amount of phase, but the same thing happens in both of these paths. So that just cancels out whatever that is. But now it's still true that now the speed in the AB path is faster than the speed in the CD path. Okay, so let's see what that implies. Next poll question. Okay, 5 seconds. Okay, we'll end there. So almost everybody said A, which is correct. The wavelength in CD is longer. That's simply because in the CD path, the particle is traveling, if the particle is in the CD path, it's traveling slower. Therefore, its momentum is O. CD, maybe I have the answer here wrong. So think through this with me. CD path, the particle is traveling slower. Momentum is proportional to speed. So momentum is smaller. So wavelength is longer, greater. So this is correct. A is correct. Wavelength is longer here and it's smaller here. Cool. Okay. So you can see what's going on then. As you tilt this thing up, you're making a bigger change of the wavelength in the upper path relative to the lower path. And what happens in the rising paths cancels out whatever it is. So the amount by which the wavelength changes will affect whether the detections are higher at C2 or higher at C3. In fact, it's a continuous, sine or cosine curve. So the amount of tilt and the strength of gravity together will determine the relative number of counts at C3 and C2. Okay, now we're changing topic a little bit. It's called the Michelson interferometer. That's different than the Mach-Zehnder. Here, I showed the picture of the Mach-Zehnder interferometer. What we're going to do is, the reason I do this is because, well, historically, Michelson was very important in the history of physics, and he used this interferometer. But secondly, later in the session today, we're going to see a Michelson interferometer in the demonstrations. Okay, so here's the Mach-Zehnder. I'm going to fold it. I'm first going to remind you that when you reflect inside red to red, you get a phase shift. All other cases give no phase shift. So there, I folded that, I folded that. We can get rid of the one beam splitter. We don't need it. We just need one beam splitter. Now we come in on this path here. The actual wave, I should annotate this. The actual wave is not a very skinny thing like that. It's a fat thing like this. And when it goes through, it's still fat, like that. So when it reflects back, it's still fat. I've just drawn the beam path separated as a visual aid. Okay, clear all the drawings. So it comes in on this path here, it transmits, reflects off of the mirror, and it comes back. Or it can come in here and reflect and then bounce off the mirror and come back. Now when it comes back, of course, it can reflect back this way or it can transmit this way. So we still have two beams coming out. It's just that this beam goes back into the source. If there's a laser here, it goes back into the laser, so you can't really measure it. We usually just look at this one beam here. Now I've shown it in this configuration with a very dim light or low probability, and up here with bright light or high probability. So I'm going to give you, 30 to 60 seconds to just think about why this one is dim. I didn't make a poll for this, so just go for it. Oh, these path lengths are equal. Okay, so make a few comments. It doesn't matter what happens at the mirrors because I assume the mirrors are identical. It doesn't matter how long these paths are because I assume the path lengths are identical. So whatever phase accumulation there is, it's the same in both paths. And the interference depends only on the relative or the different phase. So when we travel through, there's no phase shift. When we come back, if we reflect off of here, there's no phase shift because we're inside the blue side. On the other hand, if we reflect off the red, there's a 180-degree phase shift. Then when we come back through, there's no phase shift. So you see the two are out of phase here because the upper path introduced a phase shift. This path here did not introduce a phase shift. So we get destructive interference. Good. Now I have to stop this and do this. Here's a Zoom poll for you. So I want there to be 1 watt out here at the lower path and 0 watts at the upper, at this beam here. Good, okay, we have 6 answers and I'm gonna display those answers because they're very nice answers. Nothing wrong with these answers actually, turns out, because either A or B is correct. So I think it's should be clear that B is certainly correct because if I move a mirror slightly, I'm changing these paths. So if I just move one of the mirrors, I'll get a different phase accumulation on that path compared to this one. So if I move this mirror just by the right distance, I could swap these powers. Now tilting the beam splitter is a little bit less obvious, but if you think about it hard enough, you'll realize that when you tilt it or rotate a little bit, it has nothing to do with gravity, but you're changing the path lengths slightly on these two different paths. So I think, I'm not 100% sure, but I think if you do the algebra, I mean the geometry correctly, you'll see there's a small change. So I say either one is correct. Okay, but B is the important one because that we can really control that one. So we have either A or B, but there's a third answer as well. We could insert a thin piece of glass here, which is a wedge shape, and it imparts a certain amount of phase accumulation, depending on how thick it is. I can move it to a certain position. So I get 1 watt here and 0 watts there. But then if I move it like that, see, I just moved that a little bit. Now the path length is different, and there's a refractive index, which is not equal to 1. So the wave accumulates a different amount of phase shift. So this is another way to do it. And in fact, Henning will use this method in the experiment. Nice thing about it is that it's much easier experimentally to move this by, say, a millimeter or half a millimeter and control the phase change. In contrast, to move the mirror, you'd have to move it by, on a nanometer scale, 10 to the minus 9 meters, which is more difficult and more expensive apparatus to build. So this is a very nice way to change the phase shift. Okay. Now, what will happen if we move a mirror continuously and slowly? So we took out the wedge and we set it up so that we have 1 watt hitting here and 0 here. Now we have a detector. I'm going to very slowly move this mirror to the right in steps of just 10 nanometers at a time, or 1 nanometer at a time. But I'm going to step it along millions of times. So eventually it'll, or maybe hundreds of times. So eventually it will be moved by several wavelengths of distance. Pole number 6. And remember, I keep moving it. I move it a distance greater than a wavelength. Maybe I move it a net of 5 wavelengths, but smoothly. So we have a certain number of answers. What I'm going to do is relaunch the poll. And as usual, stick with your answer if you like your answer. But just the hint is I'm going to move this by, very smoothly, a total distance of 5 wavelengths. Okay, 5 seconds. Oh, that's everybody. Very good. Okay. This time, everybody almost everybody got the right answer. It will decrease and then increase and then decrease and then increase. I think the grammar here is bad, but what I mean, it'll repeat that cycle many times. The power of this detector it'll start large, it'll decrease and increase, and etc. It will oscillate like this as a function of changing this path length there. Okay. That's because this path is not changing. So the wave that's coming from this mirror down is fixed in space. It has its peaks at a certain set of peaks. But as I slide this back and forth, I'm sliding those maxima, those peaks and troughs back and forth. So they're going to slide through the fixed peaks and trough here. And I can make it interfere constructively, then destructively, then constructively, then destructively. Okay. Let's go to the Jamboard and take a look at this one. So we're on page 1 of the Jamboard for July 30th, as it says in the upper left corner. I'm sharing my screen, so you can type or write in answers. It's a little bit It's a little bit subtle. Think about what happens when the light travels to the mirror, which has been moved, and then it travels back along the same path. So the answer given may or may not be correct so far. Wait, the answer should be expressed in terms of L equals something. So not, it can't be 1/2 L. Any more votes? It's not 2x, because x is whatever it is. X is wherever you start at. But you certainly don't have to move this mirror twice that original distance all the way out to here to get the result. You just have to move it by some tiny amount to get these oscillations. And yeah, it's either, the answer is either wavelength or 1/2 a wavelength. So it looks to me like 3 against 1 so far. And the answer is 1/2 a wavelength. Good. That's because the phase accumulation depends on the total distance that you travel. So when you travel this much extra distance and go back again, you're traveling twice. The length that you travel is 2L. So if the wavelength, and if 2L is equal to the wavelength, that gives you a perfect full cycle of oscillation. So that means L equals wavelength divided by 2. Cool. Okay. Next question. Changing the topic. We're warming up now for the experimental demo. So now, how to verify by the experiment that the same interference that you could observe with a laser. So previously, I had a laser here. Now, how to verify by the experiment, maybe replace the laser with something to prove that this same apparatus will cause interference for single individual photons. Draw a picture or propose or type an answer. That's absolutely correct. Remember what the device is that allows me to split a blue photon into a pair of red photons? Or draw the picture. Right, the word herald is exactly correct. When I have 2 photons produced by splitting one blue photon into 2 red photons, if I separate those 2 red photons and detect one of them, we call that the herald. And if we get a herald click, then we know that the other photon, the twin photon, is traveling through space. There it is. I just copied from our earlier lectures of 2 weeks ago the device in question. It's called a nonlinear optical crystal. It's not a calcite, it's some other special crystal. You send a blue laser beam into here, and it produces a pair of photons, one here and one here. And if the herald clicks, then I know that there's a photon traveling over here. I'm pretty sure there is. In fact, Henning did an experiment to prove that it works pretty well. Okay, so the idea would be you send that single photon in upon the herald click, and then you put your detector here and you get a click or no click. If the photon comes this way, you get a click. If the photon travels back this way and is lost, you don't get a click. Now you're gonna move this mirror slightly back and forth, or you're gonna put a wedge in here, as Henning does, and I'm gonna move that wedge up and down and change the optical path length in this region. And I should be able to get an oscillating power in this, or oscillating probability, not power so much, but probability in this detector. So that should work, right? But there's still a problem that we talked about, and Henning emphasized that. What if there is some other light source over here? There's a light bulb over here, and it's spewing out photons. And some of those unwanted photons can get into my path here. So even if I get a click over here in my herald, I'm pretty sure that there's one nice photon that matches the herald photon, but there could be some other photons coming from the light bulb. And then if I see my nice probability curve, this is X, now I'm gonna move it. If I see my nice probability curve I expected, I'll be able to prove by an experiment that there's only one photon hitting my detector. And Henning did this experiment as well, and I talked about the theory in great detail. What did Henning do when Henning had this experiment? He had a laser. Yes, I mean, calculate G2. Remember good old G2? If G2 is 0, that means we had a single photon here. And remember how Henning did that. He went to the crystal, he had the herald, he had this going down here, and then he put in a beam splitter. It was actually a fiber beam splitter. And then he had 2 detectors here. And remember we talked about the joint probability for clicking A and B. If that probability is 0, well, if there's only one photon here, then both detectors cannot click. So the joint probability is 0. So if you measure G2 0 or very close to 0, that means that you think that you verified that you have just almost always one photon here. Good. So this is dredging up ancient history from 2 weeks ago. Ha. There's the picture that we need. Coincidence counter. Okay, time is running short, so what I'm going to do is I'm going to go straight over to Henning. If there's time left at the end, we can try a couple of other topics here. But I wanted to go nice and slow today because this is a very important thing. Okay, so what I'm going to do is I'm going to stop sharing. And Henning, are you there?
Hello, yes.
Hello,
I
Henning.
hope you can hear me. Hi.
Yeah, I hope that was a good introduction for your lecture.
Yeah, perfect, perfect. Thank you. So now you can see my face. That might not be the best thing for the rest of the session. So let's go over to some slides, and I will start with a little bit of also a little bit of a history maybe, and let's get these slides bigger. Right. Thank you. So yeah, we've in our first session we've looked at this the photon source, or the photon pair source that we have, and see what we can do with it. We've seen, and we will see this again today, what our interface looks like. And we've, as Professor Raymer has just reminded us, we've also calculated this G2 function and seen that it was rather close to 0, which meant that there were heralded single photons being produced. And last week we've looked into a little bit of a different application. There we've actually not used the single photons or the heralded single photons that we usually produce, but we've looked into the quantum key distribution aspects, and there we've used dim light pulses. Although it would, of course, be a little bit nicer to use single photons, but it also works with these dim light pulses, as Professor Raymer also discussed. Now today, let's have a look at the setup today. So let me try to give you, this is the live image. It's getting a little bit dark here already, so we'll see whether we need some additional light later. So what we're going to use is we have the same photon pair source that we've used before. Let me, maybe I have something where I could point with somehow, right? So you see this part is again, here is where the photon pairs are being produced, and this is where they're being collected into the fiber. And now we have a third setup that I will try to show you a little bit closer. And that's going to be, my mouse is someplace again, and I don't know where. Yeah. Okay. And now we're gonna use these heralded single photons and try to get them into our Michelson interferometer. And this is what I'm going to show you a little more closely. All right, so that maybe, oh, okay. So this is very dark today, so I'm going to try and use a flashlight that I have here, and please tell me if you don't see anything. So, so I hope you can see the flashlight. I also have a sort of a screwdriver here so that I can point at some things. So what's actually going to happen is that these one arm of this down conversion photon pair source is coming from here. So we only use this one arm, right? This other arm is going directly into the other detector, but this one single photon that's being heralded by the click in the other detector is coming from here. And this thing that I don't know whether you can see it very well, but this is a sort of a glass cube, and this is what's the beam splitter. So I don't think you can see this interface in this diagonal here, but that's where this beam splitter sits. And then let's say a part of the light, which is not completely correct, but let's just say it like this. If you put in a lot of light, you will see that about half of the light will be reflected into this direction. There's another mirror here. And then a part of the light is going to be transmitted into this direction, and there's another mirror here. So these are the two mirrors that we have here. And then some of the light will hopefully go into this fiber again, and this fiber then leads to the second detector. And okay, so we've also, Professor Raymer's also already discussed several possibilities to, let's go back to, oh, maybe not this one. Let's go back to this one. Right, Professor Raymer has already discussed a few ways of how we can change this phase in the interferometer now. And one way of doing this is by changing the position of one of the mirrors, right? So I hope you can see my mouse pointer here now. So if we change the position of this mirror sort of in the longitudinal direction, then we can change the phase. But and this has already been mentioned too, what we can also do is we can use this wedge window that we have introduced here and sort of change the position laterally to the beam, so that this the region that is passed through by the light is either thicker or thinner if we move it a little bit, right? So this changes what we call the optical path length. So that's basically the geometrical length times the refractive index, right? And you can see in the lower right-hand corner here, you can see that there's a slight wedge of this glass piece And this is what changes the length in this direction if we move the wedge in this direction. So it's basically just getting through a bit of a thicker or thinner piece of glass, and that changes the relative phase. Right, let me show you again where these, I hope that you can see this too. So there's actually this glass, this wedge window here that we are moving in and out like this, right? So this is a bit of a stepper motor, and this changes the position of some sort of a sliding piece here, and this moves the wedge window in this direction. Right. So let's maybe look at the count rates that we have here. So right, switch to this image maybe. So these are the count rates that we're seeing at the moment. For example, I could switch off the laser completely, then this happens. Don't see anything anymore. This green curve is always what we call coincidences, right? So it's basically the heralded single photon count rate that we see. So if I switch it off on again, this is what happens. Now I can also put something in one of the arms. So you can maybe see me put a business card in one arm. Something changes. I can put it into the other arm. Something should change too. Right, and you can also maybe think about what should change now. Should it be exactly half of it maybe, or maybe not? But we'll probably get to that later. So the next thing I can do, I can move this wedge window more or less automatically, and I've already set it up. This doesn't mean anything now, but I've already hopefully set it up. So what will happen now is that this stepper motor will go continuously in one direction, and it'll move some sort of steps. And what you see here in the in this position window, or on this x-axis, basically is the position of this wedge window, and the position is sort of laterally to the beam, right, perpendicular to the beam. So this is what this wedge window will move, but it's not what we could put in directly into the equation maybe if we would move the mirror, right? So this is not directly connected to the wavelength, for example, but we will see later how this could go. So right, it'll move something like 0.1 millimeter now, from minus 0.9 to minus 1 millimeter. These are just relative numbers. They don't mean anything. Just the relative distance means something. And the step size is something small, let's say, and we'll just start it and we can see what happens. So this is what Professor Raymer showed in this in one of his Jamboard slides just before. And what we expect is hopefully some sort of a, well, again, some sort of cosine squared function that we would hopefully see here. Right, what we also see is that we were not at a perfect constructive interference before, and that's why it when I put in one of these business cards in one of the arms, it didn't go to half of it basically. Right. Maybe while this is moving, we can also think a little bit about or see what Professor Raymer introduced just a few minutes ago, that ideally this curve would go to 0, right? Because if there's complete destructive interference and there's no background light or nothing else that somehow messes this up, then this curve would have a visibility, this is called, of 1. And this basically means that there are that the minimum is exactly at 0, right? On the y-axis, of course. Right. So now what we can do, and if this is finished, what we can do is we can try to calculate the wavelength of of the light that we're putting in there. I already mentioned that we cannot directly use the x-axis of this, but there's a bit of a formula that might look a bit more complicated there than it really is, how we can calculate this. And that's, I would explain it very simply. I don't think it's a big deal. So where does this factor 2 come from? This is also very easy because the light has to pass through this wedge window twice, right? It's exactly the same that as we had it before in this, when you move the mirror, this also sort of has twice the effect on the face, because you move it sort of, because it has to go one way out and then in again. And that's the same here. So you have this factor of 2 here because of going through the glass window twice. Then you have this n is the refractive index of this piece of glass. In our case, this is about 1.5. And you have to subtract the refractive index of air. So basically that's why it's n-1, because the refractive index of air is at least very close to 1. And then you have the angle of this wedge, and you sort of take the tangents of this, and then you have sort of the thickness or the change of the thickness of this wedge window. And this d is the distance between the maxima of our interference pattern, and this is what we see in this on this picture, right? So you can see the difference between one maximum and the second maximum, and this is not going to be very exact. This is going to be a very coarse measurement now, but here I would say this is about minus 0.975 maybe, and this is maybe something minus 935, I would say. So let me just try to find my calculator here. Where is it? Right there, you can't see it yet, right? So let's go to this maybe. Right, so now you should be able to see this. Let me go to this a little bit bigger. Right. So no, right. So I've already forgotten what I've been saying here. So you would clear this. We put in. Sorry?
The
yes.
distance you moved, I think, was 0.04 millimeters.
Okay, great. Thank you. Okay, so I will just put in this factor here from the slide, right? That was 0.0178. And then I was just reminded. And then we have 0.04, right?
Yes.
That was what, right, okay. So, and this is, okay. And that was in millimeters, right? So we had the millimeters, and that would be micron somewhere here. So we have 0.71 micron, that would be 712 nanometers, which is, you know, not so bad. It's the correct order of magnitude. It should be somewhere around 800. But while I'm making a little bit of a longer scan here, maybe you can think about where we or how we could increase this accuracy of this measurement, because it's not very accurate, right? So I think we agree with this. So I will just briefly go to some position here. We don't have to look into that very carefully, but then I will start a bit of a longer measurement, and we will see what can happen if we now go for a longer scan over a broader range. And maybe we can also already think about what we think might happen. Right, so I've just set you know, starting position and the target position and the some step size. And I've also set the integration time to a value that I think is a good one. And now we'll just have to wait for some time. And does anybody have an idea what will happen if we do this now? So we will take a lot longer. Before we had something like 2 wavelengths, right? So we've seen 2 periods of this cosine squared function. Now we're going to take a lot longer measurement over a lot longer, further distance. So does anybody have any idea what could happen? Do we see the same picture over and over again, or do we see something else?
So why does it look noisy like that?
Yeah, that's a good question. And the answer is, if you look at the left-hand side, you see that there's not a lot happening at the moment. So there's not really a lot of distance between the maximum and the minimum, right? And now you can see that this is getting bigger and bigger. And so this is also part of the, sorry, yes.
You're taking larger steps, so the oscillations look like they're shorter.
Yes, exactly. Yes. So the scale on the x-axis has changed very much, right? Before we had something like, I don't remember, 0.0 something millimeters, and now we're scaling over 2 millimeters of this wedge window.
So while we're waiting, I can give a little comment on that. Maybe let people think. Remember, although the laser is continuous, it's emitting photon pairs. One is the herald, and the other is the signal that's now going through this interferometer. And this single photon is interfering with itself in a different paths. But the point is that the photons that are emitted in this down conversion process are not monochromatic. They don't have a very sharply defined wavelength or frequency. The reason, I was going to draw a picture earlier, but now I have to say it in words. The reason is that in down conversion, when you annihilate one blue photon, you produce a pair of red photons. Well, it's not necessary that the 2 red photons have exactly the same frequency and wavelength, because you could have one red photon that has a little bit higher energy, therefore a little shorter, smaller frequency, smaller wavelength, another photon that has the complementary energy. So the point is that the energy of the 2 photons have to add up to the blue photon you annihilated. But that doesn't fix the energy of either photon, because one photon could have high energy, other one lower energy, as long as they add up correctly. So what this means is that when you herald one of the photons, you've destroyed it, and now you have your signal photon, but you don't know exactly what the frequency and the wavelength of that one photon is. It has an uncertainty. It's actually a quantum mechanical uncertainty. And in quantum mechanics, there's a Heisenberg uncertainty principle between the uncertainty in energy and the uncertainty in time. And Planck's constant is the relation, is the constant. So what that means is that since you don't know precisely the energy, there's a spread of energies for this photon. It means there's also a spread of times. And here time means a duration. So it means that this photon is, when it's produced in a packet, a wave packet, and it has a certain duration. And it could be quite short. So if you send one very short photon packet into the interferometer, think what's going to happen now if you move one of the mirrors by a very long distance. That's the region where the green trace is right now on the far left. At the center where the fringes are large, that's where the 2 paths were almost equal, but slightly varying. And on the edge is where we are now. One of the one of the arms has been, the arms of the interferometer has been made much longer than the other one. So think about what happens when the photon packet travels through this interferometer.
Yeah, exactly. And so I think the term coherence has come up before. So this is what we say when already you can already talk about that in classical optics. If you imagine light being a wave, right? So you also have something that you have a fixed phase relationship between maybe two different beams of light or something like that. In this case, you need a sort of a fixed phase relationship between, well, that's always very difficult to say, but let's say it a little bit, not perfectly correct, maybe between the one part of the photon that takes the one way and the other part of the photon that takes the other way, which is certainly something that doesn't happen like this. But you need sort of a fixed phase relationship, or yeah, a fixed phase relationship to get this interference. If you have sort of random phases between the two parts that are supposed to interfere, then you don't see any interference anymore. And this is what would also happen with a classical laser beam, let's say. Right. So, and in this case, we have a very short coherence length, as this is called, or coherence time, whatever you want to say in this case, doesn't matter. This is exactly what Professor Raymer has just said, because our photons, this is also a bit of a, well, difficult thing to say, but you can say that these photons are sort of very short. And this is why they only interfere when the path length difference are very similar. Okay, any questions so far? Maybe not, or maybe very many. So let's try to look at the different or an additional experiment, as Professor Raymer has also already introduced. Let me get back to what we want to see here. Maybe this one. Right. So what else can we do? Right. We've seen that there's interference, and we can maybe all at the same time also show that there's that we still have these single photons here, so, or the heralded single photons. So I will, if you look at the right hand side, I will add another device, and let's see. I thought I was. Okay, yes, this is what I was really wanting to show. This is also what Professor Raymer has just shown, right? You have the photon in the one arm from the down conversion entering this Michelson interferometer. Then you have the two mirrors here. And then we add another beam splitter and another one detector. So there we have 3 detectors in total, 2 behind the interferometer. And this is what I'm going to do now. You've seen me do that before when we showed that there were single photons coming out, or heralded single photons coming out from the down conversion source. So I will use the input of the beam splitter and connect that to the output, or connect, let's say it the other way around, connect the output of the beams of the interferometer to the input of this fiber beam splitter. This is what I'm doing here now. Like this. And then I will connect the outputs, the 2 outputs of this fiber beam splitter to these 2 other detectors. Right. This. Okay, we've also seen this fiber beam splitter last week when we were looking into the random number generator. Right now we're looking at something a little bit different. What? Right, so, and we're going to go to about the center where we have a lot of interference. Somewhere there, maybe minus. Right, and we take bigger steps. So they're faster. Right, and so what we can see on the, you don't see on the screen now, but I'm only, brushing through this now. So, but now you can at least imagine a little bit that there's some interference, but I'm taking 2 large steps so that we don't really see anything here. But now what we can do, we can also look at these 3 numbers again. And what we're going to do is we're going to go to the maximum, and I'm going to try to get this manually now, just to find some sort of maximum here. I'm just moving this motor by hand. It doesn't, that doesn't hurt. So just do it like this, and then we can take these numbers again. We need this one too, and we can calculate the G2 function again. So let me try to get this back. Right, so if you remember what the G2 function looked like, we have this function over here. So these are the 3-fold coincidences. In our case, they are called now 0, 1, 2. This is the heralded single photon count rate. That's the 0 channel here. And then we have the 2-fold coincidences between the herald and one output of the beam splitter and the herald of the other output of the beam splitter. Right, and I'll try to do this now. I will only go once here. If you remember last time, we've taken 10 seconds. So let's go for 10 seconds now, because you've seen this value is already 0, so I don't have to calculate anything. The other values will not go to 0, so there's no problem with dividing through 0. So this would have been just 0, but the statistical error would have been quite high. So I will take this now. So here we have 1, 3, 4, 7, 8, 1, and another one. All right, that's correct. I have the correct number of zeros, and divide them by this number first, 1, 7, 9 to 1. Divide that by 1, 3, 4 to 5. So this is again about 7 or 8% of this G2 function. So I think we're still quite convinced that these are single photons that are passing through, or heralded single photons that are passing through the Michelson interferometer. And what we can also do, we can take another point. I mean, we could basically do this now for each point of this interference curve, but that might get a bit boring in the end. So, and the 0, I mean, we can also do it at a minimum of the interference here, but that is also very boring, because almost all the values will be closer to 0, right? So that will again have a very large error, statistical error here. Right, so I've taken one other point here, and we can do the math again. Back to this number. Okay, so here we have 5 times 1, 3, 4, 5, 3, 8, 0, 5, 1, 4. Okay, and we're about 8%, and so on. And Yeah, this is all I wanted to show today. So are there any questions, please?
Well, if not, I'll resume a little bit, make a few more comments, and if people think of questions for Henning in the next few minutes, please put them in the chat window. So thank you, Henning. That was really nice. The fact that we can create single photons, herald them, put single photons through the interferometer, and then verify after they come out of the interferometer, they're still single photons. And at the same time, we see interference. So here we're seeing both the particle behavior of light as well as the wave behavior of light simultaneously in a single experiment. It's a very nice thing. And I should say that maybe 20 years ago, these kind of experiments were unknown, 25 years ago. And it's only been in the past 20 years, these experiments have really been well understood. And only in the past several years that they've been engineered to such a nice point where companies like qutools can package them into a student laboratory apparatus. And some universities are beginning to buy these apparatuses for their teaching laboratories. So let me go back and share my screen. This is where we ended up. And we talked about, Henning talked about this question. I just want to review this because I know sometimes when you're looking at apparatus demonstrations and numbers on the screen, it's hard to keep track of what's really going on. So let's review this from a more pictorial point of view. So what he had was, initially these paths were almost equal, and he was varying the length of the path by very small steps, you know, 1/10 of a wavelength or so, 100th of a wavelength, and he was able to map out this nice cosine squared function, which went almost to 0 very nicely. And then the question is, what will happen if we continue moving this mirror to a very long distance, much farther? And then he did that. And the result, it looked like this. I've chopped out the boring part, but in the middle, there was the nice oscillations, and out at the edges, there were very small oscillations. So why is this? Well, we're losing coherence. And remember, we always talk about coherence in the context of quantum physics. In order to maintain polarization states, you need coherence between the components of polarization like H and V. In order to maintain the integrity of a photon wave packet, you need a different type of coherence, but it's still coherence. And if you lose coherence in a quantum technology situation, that's called decoherence. In a quantum computer, decoherence will completely destroy the quantum nature of the quantum computer. It will no longer be a quantum computer. So this is a nice example showing using single photons how to destroy coherence. Now, it's interesting because this is not just straight up coherence, but it's actually a relative coherence. And remember that coherence really refers to quantum states. It does not refer to particles or waves. It really refers to quantum states. So we have a quantum state of light coming in here, some kind of a wave packet. And it goes in and out, goes back to these two paths. And the question is, when it goes through path A and comes out here, compared to when it goes through path B and comes out here, how do these two quantum states combine to give the final quantum state? Is there interference or not? And that requires coherence between these two paths. For example, if I were to grab this mirror and jiggle it back and forth violently during the time that Henning is doing the scan, it would just randomize this pattern and you would not have coherence and you wouldn't see any nice oscillations.